it's outrageous. The theory is outrageous. Quantum theory as a whole is wrong. It's not Einstein was wrong. Quantum mechanics is wrong.
What do consciousness, the measurement problem, and black holes have in common? With characteristic boldness, Sir Roger Penrose outlines his controversial views on the collapse of the wave function,
The Schrödinger equation, quantum theory as a whole is wrong.
the role of gravity in quantum mechanics,
The principle of equivalence, which is the basis of general relativity, is in conflict with the principle of superposition.
and his own radical theory of cyclic cosmology.
I don't believe in inflation.
That is the idea that our universe evolved from a previous universe and gives rise to another, forming an ever-repeating cycle. Penrose doesn't just poke holes in existing theories, he offers ambitious frameworks like twistor theory that could potentially unify quantum theory with general relativity. My name is Kurt Jaimungal. This episode was filmed on location at the Math Institute at Oxford, directly after our interview at the Institute for Arts and Ideas. It's a rare in-person glimpse into one of the most influential mathematicians and physicists of the 20th century. Sir Roger Penrose, it's been a long time coming. I've been a huge fan for, I think, decades, literally decades. Thank you and welcome.
My pleasure.
Good meeting you at the Institute for Arts and Ideas.
Lots of people don't believe some of them.
The arts and ideas? What do you mean?
Well, the ideas about cosmology, which I have, which are certainly, people have a lot of trouble believing them. Even though we have good evidence, yeah. But still, never mind.
Is that the torch that you want passed on most? The conformal cyclic cosmology?
Well, I have a trouble because there's more than one thing. You see, one of the things is twistor theory and its progeny. There's been a conference. You see, this is taken seriously in the sense that there has been a conference going on all about twistor theory. Not just a conference, but a whole, I think, of a whole term, I think, dedicated to the subject of twistor theory, which is something which I sort of started in 1963, I think it was. And it's had many developments and many offspring, you might say. And it's spread out to have interest in different areas. Now, it's one of the things that I've been working on for most of my life. And I can't explain it without being a little technical. It's just that...
You can feel free to be technical on this podcast.
Okay. It's a bit like... Well, Hamilton discovered quaternions, which was a way of talking about the geometry of three space, and he introduced this thing called the vector product, which if you have two vectors, well, it's really an algebra of vectors, where you have vectors and scalars mixed together, and if you multiply two vectors, you have this thing called a cross product, which gives you a third vector. Now, this kind of notion is coming in at a different level with what I call twistors, or now what I call bitwistors. See, the twistors, the subject took ages to develop. As I say, 1963, when I first had the concept, so I gave a talk in Cambridge just recently, where I explained the origin of the ideas, and there's a certain, you might call it, slight misconception. There are two different concepts which get confused in twistor theory. And these two concepts are positive and negative frequency and positive and negative helicity.
Mm-hmm.
And the thing is that the positive negative frequency idea was something that I learned from Engelbert Schucking, who was somebody I shared an office with when I was in a group of people working on general relativity in Syracuse, New York State, in the United States. And there were a lot of people working on relativity theory there, and this was, I think, in 1962. And I learned from Engelbert Schucking two things which I found very interesting. One of them was this question of what you mean by what's important in quantum field theory. And he said the most important thing in quantum field theory is the splitting of field amplitudes into their positive and negative frequency parts. You keep the positive frequency and you throw away the negative frequency. And I thought, gosh, that's an interesting idea. The other thing he told me was, and he told me various things, but these were the things of relevance to what I'm saying. The other thing he said was to do with the Maxwell field equations. Maxwell's equations, which are very important. They describe electricity, magnetism, and light. So it's a theory of light as well as how electric and magnetic fields interrelate to each other. Very beautiful equations, which I learned about when I was a graduate student. And I was very keen on the Maxwell equations, especially when you write them in this formalism called two-spinor formalism, which is I can say a bit more about later. But the Maxwell equations, he told me they are conformally invariant. So they only depend on space-time structure independent of the scaling. So if you magnify the scale up or down, magnify the metric up or down, if you like, it makes no difference. That's conformally equivalent. So the conformal maps are ones, or the conformal transformations are ones which can change the scale, but they don't change the light cones in special relativity terms. So the speed of light is the same. Of course, light, after all, the speed of light is the same when you magnify and change the scale. But what struck me about these two facts that I learned from him, is there seemed to be a little of an impasse between the two. I mean, how do you decide what splitting the positive and negative frequency? You look at the individual frequencies, which means you do a Fourier decomposition, and you take each individual Fourier component and you split that into its positive and negative parts. That's not conformally invariant. You do a conformal map, conformal rescaling, the Fourier decomposition does not go into itself. And so I thought it would be lovely to have a way of looking at this, which is they come together and you don't have this sort of impasse between the two. Well, I was aware, I don't know whether I was told or I thought about it myself, I was aware of the fact that if you take the field of complex numbers, fold them up into a sphere, so you've got a point at infinity as well, and you take the real numbers and think of that as the equator. So the real numbers go around the equator, and the complex numbers go up and down. And if you have a function which is defined on the equator, which extends into one hemisphere, that's positive frequency. If it extends into the other hemisphere, it's negative frequency. This is a completely conformally invariant description. You conformally invariant the sphere, and it doesn't change the splitting into two halves. So I wanted a way of doing this, but globally for space-time. So for the whole space-time, I wanted it to be somehow that the real space-time is the boundary between two extensions into the complex. But if you just complexify space-time, make all your coordinates complex, you get an 8-dimensional space, not a 5-dimensional space. So that's no good. It doesn't split it into two halves at all. You get a thing called the forward tube, which is a little tiny thing at one side or the other, in which you can talk about things being regular there or not, but it doesn't split anything in half in the same sort of way. So it didn't satisfy me. I don't know why. I mean, what was I doing? It didn't seem to have any rational reason for looking at this. But it did seem to me there ought to be a way of exploiting this beautiful way in which you do the positive and negative frequency without having to look at the Fourier components individually. It's a deeper concept, if you like, and it's also conformally invariant. So the scale business that Maxwell theory has, you don't lose that. Okay, well, I had this sort of going around in my mind and didn't know what to do about it. It was a very unfortunate occasion because I was in Texas, in Austin, Texas, and I was working with various colleagues in Austin, Texas. Engelbert Schucking was running this particular meeting. It was a year-long meeting where people like Roy Kerr, Ray Sachs were there too, and very distinguished people working on relativity theory. And there were also people in Dallas, Texas, and one of them in particular was somebody I was collaborating on a book. I don't think I was doing it at that time, on spinors, and this was Wolfgang Windler. And Ivor Robinson, he was somebody who was a very clever fellow, had wonderful ideas. He never wrote anything down. He relied on getting a co-author to write the paper. It was all done with words. He was had a wonderful way with words. The Americans loved him because he spoke in this way that they weren't used to, which the words all fitted together in this beautiful way. Yes, he did have a wonderful way with words. There's no doubt about it.
Was he the one that didn't write papers?
Yes. But he was important in another story, which is a different story, with my story, namely the singularity theorem, because that was walking down the street and crossing the road. That's a different story. It was the same person. That was Ivor Robinson. Yes. So he obviously was somebody who could take my attention. But what he had told me about was he'd found some solutions of Maxwell's equations, which had a very special character. They're what are called null. They have point in one direction. You see, usually there you have these two directions, which are called principal null directions, on the light cone. They're light directions. And if they coincide, it's what's called null. And these are more like radiation fields. And he found a beautiful family of solutions, which he constructed in the following strange way. You take a light ray, one light ray, and you take all the light rays which meet it. When I say a light ray, I mean the trajectory of a photon. So in space-time, it's the space-time picture of a photon. That's thought of as a particle. So now if you think of one light ray, and you look at all the light rays which meet it coming in, then you have a family of light rays. But they're light. And then he constructs this solution, which is based on those light rays. Now, they have this awkward singularity, which is the light ray that they meet.
Why is that a singularity?
Well, they all start coming together, and so they're not... The nature of the solution is different when they come together. You see,
okay, but it's of a different sort of singularity than the singularity theorem.
It's not a serious singularity. It's a singularity in the Maxwell. I think things become infinite.
I see.
I don't remember the details of it.
Sure.
They just become infinite of that solution. Just because the light rays don't make this nice family anymore, they've got crunched up on the other light ray. But what Ivor Robinson did, he had this clever trick where you just place the light ray into the complex, make it a complex light ray, then you can keep the light rays which meet it. There's a family which is still real. So you can see those real ones, even though the one they meet is in the complex. And they twist around each other in this wonderful configuration. I thought about this before, and I think I knew in detail what this configuration was. It corresponds to what's called Clifford parallels. Clifford parallels are a beautiful geometrical configuration. If you take a three-sphere, so that's an ordinary sphere, but in 4 dimensions. So it's a three-dimensional surface in 4 dimensions. So it's a family of points which have the same distance from the origin in 4 Euclidean dimensions. I'm not talking about space-time now. That 4 Euclidean dimensions. So you have a three-sphere, and there's this beautiful family of circles which fill the whole three-sphere. No two of them intersect, and they all link each other. It's called Clifford parallels, or it has a name which is the topological people like better. Well, it's called the fibration.
Right.
And it's a sphere's worth of circles. It's a very nice example of a fiber bundle, and how you have this diagram that people like to draw, where you have the fiber, which is the circle, and the bundle, the entire bundle is the sphere, and the projection down is the two-sphere. So each circle corresponds to a point on a two-dimension, an ordinary two-sphere, an ordinary sphere. So the points, each point corresponds to a circle. So it's a beautiful example of a fiber bundle. It's the one most simple and beautiful example you can have in a way. I was well aware of it. I just liked the geometry. I found it was really elegant. And it's the same kind of thing you get with these, except that now you're talking about light rays. So if you think of the light rays, not sure quite the easiest way to say this is, it's now the circles correspond to each point of the Clifford three-sphere corresponds to a light ray. And the whole family of them twists around in this complicated way. So I was familiar with this configuration. And that this was a sort of way of thinking about a complex light ray. You push it into the complex and you get this real description of it, which somehow feels out this complex light ray, but only in this real configuration that you can visualize. So I found this very beautiful. Now, is this any use to me? Well, the occasion that I'm talking about here was a particular occasion, which was maybe in a sense, the most significant thought which I had had, which was, well, there was an event, you see, very unfortunate event when Kennedy was assassinated. And this was in 1963, and it was in Dallas. And my Dallas colleagues, including Wolfgang Rindler and Ivor Robinson and other people there, Oshvarts, Pishta Oshvart was there, and they were at a dinner. And Kennedy was supposed to go and give a talk at this dinner. And he was awfully late, and they sort of joked, well, maybe somebody shot him. Somebody had shot him. And they came, and it was a way of, so as they came, it was just about a week later, I think, when we decided to go to southern Texas, to go to a nice place where there was a beach and people could relax and try and recover from this awful occasion. And
do some math?
So we went down there. I don't think we taught much maths, I don't remember. But I remember coming back, and most of the people wanted to talk gossip with each other, including my then wife. They really wanted to gossip. I wasn't interested in the gossip. I just wanted some peace. And I was the one who was committed, Morris committed to be in the car driven by Pishta Oshvart. Now, the thing about Pishta Oshvart, he was a Hungarian who did speak English, but he didn't like to speak, even in Hungarian, I think. He didn't like speaking. He was a silent person.
Okay, he was the Hungarian Dirac.
Yes, but he was definitely, he could speak English, but with a strong Hungarian accent,
sure.
Of course. And he was the driver of the car that I came in. So this was very nice for me because I didn't have to make up conversation to speak to him. He preferred not to have conversation. So I think to myself, I knew about this Robinson congruence of rays, which sort of describe a light ray, but which has been displaced in this way. And I said, the thing to do is to count, and I thought, I didn't say anything, to count the number of degrees of freedom this configuration has. How much freedom does it have? And I counted them, and it has 6 degrees of freedom.
And that's significant because?
Yes, this is very significant because light rays themselves have 5 degrees of freedom. So it's only one. You make your light ray complex in this sense, and you only drop your dimensionality by 1. It's not really what you do if you complex every light. We 5 complex dimensions. No. This only drops it by 1. Why is that so important to me? Because this gives me a picture. The light rays themselves are represented by points on this this 5-dimensional boundary, and the Robinson congruences, as I call them, these twisting congruences of light rays, represent the points. If they go right-handed, they're one side, and if they go left-handed, they're other side. This is the splitting of the space into 2 halves, just what I was looking for. Only it does it globally for the whole of space-time. Don't think of points, think of light rays. And then the complex ones, in this strange contorted sense, are only one more dimension. So that was the origin of twistor theory. I got him back much earlier than anybody else, because they were still gossiping, I guess. And I went to I had a blackboard there, and I worked it out in terms of 2-component spinners, and it worked beautifully. And this was twistors. You take 2 2-component spinners. The way you can think of it, see a 2-component spinner ordinarily points along the light cone. It's like a light. It has a null vector associated with it. And that null vector points along the light cone. In addition, there's a little flag plane, and the flag plane tells you its phase. So the length of not the length, but the sort of extent of the light ray, or the extent of the null vector gives you one scale, and the other scale is the phase, which is the little flag plane. So you have this nice geometrical way apart from the sign, which you have to add in addition, you've got the nice way of describing two-component spinors. I was well familiar with that. So the thing about the twistors, as you can think of the light ray, where does it hit the light cone of the origin? Some point. And then you look at the light ray going up, it hits that point. That's the thing I called omega. I didn't call it omega at the time, but it's to do with angular momentum, really. It's the moment of the light ray about the origin, and the other is pi. That's the momentum of the photon. So you've got the momentum and the moment, and they're two-component spinors. They give you a four-dimensional entity. This was a twistor. So that was the origin of twistor theory. I tried to talk about it to my colleagues there. None of them were interested. Engelbert was. He was the only one that was at all interested in what I'd done. So it was a little bit of a...
Why weren't they interested?
Because it wasn't general relativity. I didn't know how to do general relativity with twistors. It took me decades to find out how to do general relativity with twistors.
Do you think twistors will be an ingredient in a theory of everything? So something that combines the standard model?
It certainly should have a much broader application. But you see, what you have to do is take another step, which I sort of made a couple of years ago, made it in a slightly different way. Well, it was a couple of years ago, yeah. But it was in a slightly different way about six years ago. Because I wrote an article then, which wasn't published too much later. But the article I wrote more recently was in honor of C.N. Yang, the great physicist, one of the people who got a Nobel Prize for weak interactions and their chirality, light ref, right? I mean, it's quite curious because of that too. You see, you have the chirality. See, when I say the twistor has a chirality to it automatically, which is the way it's described. Right. If you reflect it, it's really goes into something else. It goes into a dual twistor. So you have a twistor, which is a four complex dimensional space, vector space, if you like. The dual of that space is the opposite twist. So you have a twistor and a dual twistor, and they twist the opposite way, roughly speaking. But this was all to do with, I was trying to do positive and negative helicity. I learned not too long after this, that you can describe momentum and angular momentum in terms of twistors very nicely. And the null ones, if you're talking about light rays, this is just a twistor, basically. It's a twistor and a dual twistor together. But the nice thing, you can describe the angular momentum. This is the notation I use later to call the moment an angular momentum thing. That's the omega. And the momentum is the other one, which is the pi part. And that's just the splitting which gives you these two interpretations. For the two parts, these have two-component spinors, and they give you these two parts. It's also conformally invariant. The conformal transformations work beautifully. Conformal invariance. It got more mixed up with positive and negative helicity. You see, what you really see is that the twistor, the positive and negative, you have the space, which is split into two halves. The space, incidentally, is a well-known space to geometers. It's a complex projective 3-space. So it's a 6th real-dimensional space, which is really complex 3-dimensional space. So it's nice to visualize because you just think of it as 3 dimensions, and you say, well, it's really complex too. So you can visualize lots of things in that. And it's really 6 real dimensions, and the 5 dimensions go either up or down, depending upon what is it that's positive or negative. Well, you look at it took a lot of time to analyze this, but when you really see its connection with angular momentum and so on, it really is the helicity. So it's to do with whether the photon is rotating right-handed, if that's right-handed, or left-handed.
So twistors are inherently chiral.
They're inherently chiral. So that this was where it was. I talked about helicity. That's what it was at that time, whereas the intention was this should be positive, negative frequency. So the whole subject kind of got mired, in my view, with this confusion. And it got particularly so when one started to talk about general relativity, and there were some ideas which came from Ted Newman, who was a close colleague of mine, and he was interested in making space-time a little complex and looking at angular momentums, things which come from your displacement into the complex. It was a very deep insight that he had there. And I realized that that was the sort of thing I was doing. And one of his ideas, I won't go into the details, I realized you could take this and talk about them in twistor terms. And this described a kind of twistor, which actually referred to a curved space-time.
Okay, wait. When you say you talked about them in twistor terms, what do you mean? The complex space-time in twistor terms?
Yes, it is a complex space-time. And you see, Ted Newman didn't mind about his space-time not being directly physical. I don't know whether he minded or not. He called it H-space. He had a construction which involved making space-time complex and looking at it in this particular way that he did.
So why was that interesting to you? Because when we've talked off air, if I mention the word supersymmetry, there's a grimace on your face.
Yes, exactly.
If I mention string theory, because it has extra dimensions and maybe some other flavors, there's an even worse grimace.
I can tell you where the grimace comes from. See, all these things are adding extra dimensions to space-time. Now, what I was doing was absolutely crucially tied to the space-time having 3 space and 1 time dimension. If you change that, you wreck the theory.
So some people see a theory that works in n dimensions, especially mathematicians, that's a feature, that it can work in any dimension. And if you say, my theory only works in 4 dimensions, some people see that as a weakness. You see that as, no, that's a strength.
Absolutely. That is absolutely the point. I'm seeing it as a strength because you're not looking at mathematics. Okay, mathematicians pick up on twistor theory and they generalize it to higher dimensions and all sorts of things. Fine, that's good stuff, but it's pure mathematics. I'm interested here in specifically the mathematics which applies to the physical world.
Mm-hmm.
Now that, whether you can generalize that to 17 dimensions is of no particular interest to me. And if people do string theory, initially when I heard about string theory, I thought it was a beautiful idea. And then when it went and they said, oh no, it only works in, I think, 26 dimensions originally, I thought, okay, that's not... Okay, you can work on that. I'm not going to work on that. It's not physics anymore.
So you mentioned C and Yang, you mentioned fiber bundles and implicitly Hopf vibrations. Those are differential geometric ideas.
Yes.
And the standard model and general relativity are based in differential geometry.
Yeah, well, standard model is not even differential geometry. It's really flat space-time, really.
Do you see differential geometry as what will be the language of physics in the next few decades? Or do you think you started off in algebraic geometry? Do you see algebraic as the chopped liver that should be...
You're talking about my shady history here. Now, it is true that when I went to Cambridge...
I'm going to ask about Grothendieck soon.
Don't. Well, you can if you like. But all is like saying, yes. You see, when I was in Cambridge doing algebraic geometry, I was trying to solve a problem that my supervisor, William Hodge, had suggested. He had given a list of problems, blah, 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 blah. And he said, you can work on any of these. And I didn't understand any of them. Oh, the bottom one I can understand. Yeah, I'll try that one, you see. I suspect it was the one that he was least interested in. I'm not sure. I think he was quite interested in it. But it was not part of the march of algebraic geometry and what my close colleague at that time, Michael Atiyah, would have been doing. He was the real expert on these things. I mean, all these things are driven by anecdotes, I'm afraid. You see, Hodge suggested at one time, there were various people in my group, and for one reason or another, they didn't sort of connect with what I was doing. But he suggested, well, maybe you're not so keen, Hodge is suggesting, maybe you're not so keen on the subject. I was expressing some disappointment with it, I think. He said, okay, but maybe you prefer to work on one of the other topics. You might like to sit in on one of the other graduate students. So I did. I sat in on this class, and I didn't understand a single word that went on. It was way above anything I knew at all.
Uh-huh.
And I thought, this graduate student, if they're all like that, what am I doing here? What I didn't realize is that graduate student was Michael Atiyah. Michael Atiyah was later to become a Fields medalist, become one of the first winner of there's another prize, mathematics prize, but the
Dirac medal?
No, it's a play on Nobel, but it's somebody else.
Abel?
Arbel Prize, that's right. The Arbel Prize. He was one of the earliest winners of the Arbel Prize. And he became president of the Royal Society. Anyway, he was obviously not your average student. It's what I mean. The fact that he he became very important in my life later on by telling me that things I was trying to do were really cohomology, which I had no knowledge about. When I found this way of doing integrals for finding, yes, I was interested in this, just what I was trying to say in a way, the solutions that Ted Newman had found, and I tried to convert them into twistor theory, which I realized you could do in a way, but by making twistor theory curved. And you can make it curved provided you don't have any what I've later called alpha planes. I mean, when you don't have beta, you have alpha planes. I've said it the wrong way. But as long as you have alpha planes. Alpha planes are things which can only exist if half of the conformal curvature vanishes. When I say half, it's a bit difficult to do that in space-time for space because the signature is wrong. You can do it for the kinds of space geometries, four geometries that mathematicians like, because the signature is right for them. You have got all pluses. You take your metric, it's all got pluses. And they like that. And that gives you a nice theory, and you can make that what's called anti-self dual. If the Weyl curvature, that's the conformal curvature, it splits into two parts, make one part zero and the other part still exists, and you get these curved solutions. If you try to do that with space-times, and if they were real space-times, you can't. Well, you can, but it doesn't get you very far, because the Weyl curvature, the two parts, one is the complex conjugate of the other. So if one of them is zero, the other one is zero. So it's conformally flat. It's not interesting as a conformal manifold. However, Ted Newman didn't worry about these things. That was my Pittsburgh colleague, who I did a lot of work with. He was a very inspiring character, and he had this idea of sort of complexifying space in a way which was sort of half doing it. And in that half doing it way, you could see that you could do what I was trying to do. And this led to what I referred to later as the nonlinear graviton. It's a complex space-time for which this Weyl curvature part does vanish. And so you can do twistor theory in it. In this complex space-time, you say, what's it good for in physics? Well, what's complex naturally in physics? Wave functions. So if you're doing complex stuff, you could be doing quantum theory. So this could be a wave function of a crazy sort. So it's what I used to call a nonlinear graviton. So it's the wave function of a graviton, but it's not the ordinary linear wave function. You see, normal quantum mechanics is linear. You can add one wave function to another, and the whole point about, well, not the whole point, but the big point about quantum mechanics is that you have this superposition principle. You can add states together. The wave function is a linear thing. You can add them. Now, this thing was a nonlinear thing. You can't add one solution to another. It's just a solution. It's a complex solution of the vacuum Einstein equations, which has this twist to it, and the Weyl curvature vanishes, and you have twistors. The kind of twistors you have are a new kind, which are curved. So you can have these curved twistors. It makes sense. However, it's a bit stuck if you want to have your physics out of it, because it's to do with this conflict or confusion, I would say, in twistor theory. It's inbuilt into the whole subject. You see, positive and negative frequency is what I was striving for, and I sort of haven't got to that because I got a little confusion in my discussion here. But you see, it does turn out to do positive and negative frequency. It took a long time for me to see that. I was driven to positive and negative helicity. You could see that almost directly. The photons twist one way or the other way. And that's what classical twistor theory does for you. But then if you start to do integrals and things like that, you can see it's a little bit more confused. And then you can see these integral things you're doing are really wave functions. And if they're wave functions, then they can have positive and negative separately. Frequency, the right-handed, they can be right-handed or left-handed, depending on whether it's twisters or dual twisters, and they can be positive frequency as well. But you've got to talk to them about complex solutions. So it's this confusion between the two, which in a sense limited twistor theory to the situations in which you have alpha planes. Now, I haven't said what an alpha plane is, but these are integral. The vanishing of this half of the Weyl curvature is the integrability condition for the existence of alpha planes. So that if you have the alpha planes, they are the twisters. So if a plane has alpha planes, each alpha plane is associated with a twister. And that's the geometrical description. But real space-time doesn't have any alpha planes in it. It's only much more recently I considered what you do. You consider what I call bitwisters. Now, bitwisters I described in a paper which was in honor of C.N. Yang. I very much delayed with this paper because I was trying to work things out. And it came out, well, it's in honor of C.N. Yang's 100th birthday, I should say. He's still alive as far as I'm aware. This was 2 years ago or something, so it came out. So I wrote this paper, which was about bitwisters and about the connection with split octonions. See, I mentioned right at the beginning the Hamiltonian quaternions.
Right.
And you have the analog of that. When you go up, these are things called octonions. It didn't take long after Hamiltonian produced his quaternions when several people independently discovered this generalization to these 8-dimensional things, which are called octonions. I was aware of the octonions, and I was aware that there were split ones as well, where you have 4 plus signs and 4 minus signs. And I thought maybe there's something to do with twistor theory there. I didn't know what it was.
That was just a hunch at that point?
Well, this was what this paper was really the result, because I could see how to do it. You can actually describe the split octonions. You have to have a product now. Going back to what I said at the beginning, quaternions, you take 2, product of 2 gives you a third. Now it's a product of 3 things, give you a fourth. You make one, you choose another element, make it the unit element, and then this other 2 gives you the split octonion product. So it does give you the split octonions. I'd only vaguely thought maybe there's some connection at one time, and later, see, it really does. It gives you the split octonions. But for that, you really need these things called bitwisters. You've got to combine a twister and a dual twister. Otherwise, these things don't even exist. So it's got to be that combination, and you have a bigger space. But what's nice about it from the physics point of view is you sort of got rid of this inherent twist into the theory. They're not really twisters in the sense that the twist goes one way rather than the other. So it removed this awkward confusion between helicity and frequency. You see, positive frequency and positive helicity are 2 different concepts. But in twistor theory, they're confused as being the same.
So I want to ask about definitions, because when you're an undergrad, people tend to think that you focus on proofs and that's what it is to be a researcher. And Grothendieck said that what's more important are definitions. So he would say you keep your definitions convoluted and you make your proofs simple.
Yeah.
What makes a good definition in physics, though?
But going back to Grothendieck, you see, there was this, when I was talking about my period in Cambridge, I was really an outsider working on this particular problem that Hodge had suggested. Although it was a bit like twistor theory in a way. You see, if you want to describe a curve, and a twisted cubic is a good example. It's a twisted cubic, you don't have one equation for it. You can think of it as the intersection of 2 quadrics where you throw away a line. The normal intersection is a quartic surface. You specialize it so it's a line and a cubic, and that cubic is called a twisted cubic. It's not the intersection of 2 hypersurfaces. But can you write down an equation for it? Yes, you can. You think of your space of straight lines, and those straight lines which meet the curve is one condition, and that gives you a formula. And this is the Cayley form thing. And that's what I was actually working on. Not that, but how do you do that in higher dimensions? How do you work out how things intersect and stuff like that? And it got rather too messy. So I had to develop a diagrammatic notation for handling all the complications. That's another story too. I won't tell you that one now. But anyway,
Grothendieck.
Grothendieck was the big high priest of all. I think initially it was it sort of crept up before you got to Grothendieck. He was the real high priest, and that's what people like Atiyah were doing and making it more and more abstract as he went on. I was going on a completely different route. I was thinking about, okay,
something concrete.
Well, it was much more concrete. Yes, I mean I could think of light rays meeting curves, or no, not light rays. I mean straight lines meeting curves, my problem was of that character, but you do that in higher dimensions.
Yeah, there's a phrase, abstract nonsense. Have you heard of that? About
Indeed.
category theory?
Oh, sure. That's right. That's the whole...
That's your feeling as well?
The whole move of, you see that, yeah, that's what they were all doing.
To this day?
That's what Michael Atiyah was a great expert in that subject. Oh, yeah. And Grothendieck was a greater expert. Well, there was a sort of Grothendieck was he went off and sort of worked in isolation and disappeared from the
Sure. What do you see as the tension between gravity and quantum mechanics? So you mentioned linear.
Yes.
Some people think one is nonlinear and the other is linear, and that's where the tension is. Some people say it's non-commuting variables on one side and then commuting variables on the other.
There is a big tension.
Observable, sorry.
Yes. But there's a worse tension. You see, there's a tension in the sense that general relativity is not really linear. It's non-linear, you see. And people like, in quantum mechanics, they like linear things. They don't care how many dimensions it is. It could be a million dimensions. It could be infinite number of dimensions. Lots of things are. They love infinite dimensions. That's fine in quantum theory. But space-time has got 3 plus 1. It's from that point of view, it's pretty boring. It's only got a finite number of dimensions. But the space-time has, and Einstein, of course, well, he got his Nobel Prize for quantum mechanics, of course, for the photoelectric effect, which has nothing to do with GR. But he was...
some people, some physicists even, like to say Einstein was wrong. They like to tout that. They like to write that on a T-shirt.
Well, they were all saying that then. You see, that was nothing new in those days. Einstein's general... Well, no, it was... Of course, it was the Eddington expedition, which suddenly startled everybody to show the bending of light was in agreement with Einstein's theory. And that did change things. It made Einstein a big celebrity, too. So that was a big thing. But it didn't really make... The quantum field theory or quantum people didn't like curved spaces because they're all flat spaces. They may have infinite dimensions, but they're flat as a pancake. They don't fit in very well with the basis of general relativity. And then perhaps you want me to go in that other route, because there's another way they don't fit in together, which is another thing. It's not so much twistor theory as it stands, but it's an important thing.
Consciousness?
Well,
Collapse?
That too. Collapse. Yes, there's consciousness, but that's... Oh, dear. There are too many stories here.
We're going to talk about consciousness as well. Let's stick with the collapse for now.
No, the collapse is important. We have to do that first anyway. You see, I always thought that I didn't like the collapse of the wave function as being... I mean, it was so... Quantum theory was terribly confused. You see, you've got the beautiful... Well, think of the Schrödinger equation. Schrödinger was as confused. I mean, he understood why he was confused. I mean, he was absolutely on the ball. But lots of people were confused. Anyway, let me not go into that story. You say, take a quantum system. How do you describe it? You take the wave function, or vector in Hilbert space or something. It's a wave function. You take the wave function. How does that evolve in time? Schrödinger equation. So it evolves in time, according to the Schrödinger equation. Is that the way the world evolves in time? No, it doesn't, because you cheat. You say, no, you've got to a certain point and you make a measurement. What does making a measurement mean? I don't know. People have funny ideas about making a measurement. The trouble is the word observation, I think, crept in there a little too...
Too sneakily, too early?
Too sneakily, too strongly, I would say. Because people think, as many, one of the big proponents of this view was Wigner, Eugene Wigner. And I actually, when I was in Princeton, I did talk to Wigner about it. I had a long lunch talk with him, and I talked about this issue of does the wave function, consciousness, if you like, collapsed the wave function, because that was the Wigner view. He was not so dogmatic about that view as I was expecting. He was saying it's a view, but a point of view. I don't think, for many reasons, it really makes sense. But it was nevertheless, I think a lot of people, even von Neumann, seemed to have that sort of idea too. A lot of people had the idea that it was a conscious being observing the system, which somehow changes the rules. You change your wave function and write it down as a in terms of its certain basis, and then you give the amplitudes, and then you look at these complex amplitudes, square them.
Yes.
Square the modulus, and that makes your probabilities.
So then what would they say, not to take you off track, but what would they say is what observes the observer?
And I don't say any of that, you see. I don't care what they say. I don't know what they say, because it's not what I say. And I think it's wrong. So although I think consciousness relates to it, Christian, it's in a completely different way. It's not what collapses the wave function. What collapses the wave function is physics. So there is something in physics which collapses the wave function. The Schrödinger equation, quantum theory as a whole, is wrong. It's not Einstein was wrong. Quantum mechanics is wrong. Now, I say this very blatantly because it's a blatant topic. I mean, Einstein and Schrödinger were much more polite. They said it was incomplete.
Mm-hmm.
Okay. Incomplete means wrong.
But you're telling it like it is.
Yeah, you've got to change it so it's wrong. But incomplete is a more polite way of saying it's wrong. Okay, they're fine. I should be polite sometimes too to quantum mechanics. Although it's pretty robust as it is. It doesn't mind people like me being rude to it. But anyway, so Einstein and Schrödinger both thought that it was wrong, that the theory needed some amendment, could be an important amendment which changes the nature of the whole subject, quite likely.
As you know, on Theories of Everything, we delve into some of the most reality-spiraling concepts from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the exact topics explored here, and even more. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's the latest in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in. And now back to our explorations of the mysteries of the universe.
Could be an important amendment which changes the nature of the whole subject, quite likely.
So you think both Einstein's, both general relativity and quantum mechanics need to be modified? Or
yes.
primarily quantum mechanics? And a tinge to general relativity.
I would say more importantly, quantum mechanics. You see, people sometimes say to combine these two great theories, you've got to quantize general relativity.
And can you explain, what does it mean to quantize?
You mean to haul it into the framework of quantum theory. So you make it into a Hilbert space and operators and goodness know what.
And you sum over metrics. Or some over geometry.
Well, lots of people were trying to. Wheeler was trying to do that when I was in Princeton. Lots of people were trying to do that. Bryce DeWitt was certainly trying to do that.
And so when you speak to string theorists, they would say, well, that's quite obviously the approach. We're the only finite quantum gravity game in town.
To do it, yes. I mean, there's nothing wrong with quantizing gravity. It's just the weak, I don't know what I'd say. I'll read the right adjective. But
You don't have to be polite anymore.
No, I'm not trying to be polite here. I'm trying to be more illustrative of what I mean. I sometimes talk about a planet, a distant planet, which has an atmosphere on it. just like it's a planet very much like the Earth, almost identical. And this spaceship, there's a space probe going out to look at it because it's very interesting because it's just like the Earth. However, there is no life on it. No life has ever evolved on it. There are no butterflies to flap their wings, and weather is supposed to be a chaotic thing, and so even sensitive to the flapping of a butterfly's wing. There aren't any butterflies on this planet. There's no conscious beings on that planet. So all the different weathers that they might have on that planet all coexist in superposition. It's a mess. The probe is going out to take a photo. It takes a photograph of this mess. It comes back to the Earth, and when it's within distance of being able to send signals to the Earth, somebody's sitting against the screen, and finally the first picture of the weather on that planet, and this person looks at it, snap. His consciousness or her consciousness makes that world into one weather. What could be more absurd? Absolutely ridiculous. Light doesn't have any interest in us. Why does its weather become one? Just because this chap hasn't taken a photograph of it. Absolute nonsense. I'm just trying to emphasize that I don't believe it is consciousness that collapses the wave function.
Instead, it's the collapse of the wave function that produces consciousness?
Well, that's my other story, which I think is another story, and is a story which I also try to pursue to some degree. I don't regard it as what I do most in my life because it's too much biology and things like that, which I don't know anything about.
Are you wedded to microtubules being the mechanism or the place? Or are you just saying, look, if it's going to occur, it needs to occur somewhere in the brain. This chap named Stuart Hameroff put up his hand and say, it could be microtubules. I found this in the brain. And then you said, okay, well, maybe.
That's more or less it, yeah. Yes, it wasn't quite like that. But I do think microtubules are a good candidate for various reasons.
But you wouldn't be heartbroken if it turned out to be some other structure?
Heartbroken is too strong. I'd be a bit disappointed, yes.
Oh.
Because I think microtubules, there are various features of microtubules I find fascinating. I don't think it's a coincidence.
Did you see the recent news about the superradiance in microtubules?
I did hear something. I didn't see it. Was that on the...
It said that there are quantum effects that are coherent in microtubules. Now,
yeah, there better be, yes.
Do you feel vindicated from that?
The trouble is I did look at the paper which was referred... I think if it's the same one you're talking about. I did look at the paper. Stuart is mentioned. There is a reference to his, but it doesn't really talk about his stuff. It looks like something else. I don't know. It might be connected. Look, I'm not a biologist, so I'm not even a chemist. I find chemist is too difficult for chemistry. It's full of words that I can't remember.
Yeah, same.
I was supposed to be a doctor. My parents were both doctors. They thought I should be a doctor. They were both medically trained. I was the one they thought would be the doctor. They won in the end because my little sister eventually got a doctor and she married one too. So they got two for the price of one. No, I disappointed them terribly. I would have been hopeless because I don't remember names, these things. You can tell I forget them immediately. I'd have been putting the wrong prescription on people's...
Well, you invented quite a few. Bi-twisters, dual twisters, alpha planes,
I remember
planes.
them more... Well, yes. I remember most of those more easily, yes.
So I'm jumping ahead because the audience is familiar with that gravity has something to do with the collapse of the wave function.
Let me make that a little more specific.
Sure.
You see, I wasn't so clear on that until much more later, I think, just a little before the turn of the century. I can't quite remember when. It took me a little while before I actually wrote the paper on it. I wrote a paper on it, which was to explain a conflict between the two basic principles, one of general relativity, the other of quantum mechanics. What's the basic principle of general relativity? It's the principle of equivalence, which Einstein admitted. Well, he didn't give Galileo credit. I think he should have given a reference to Galileo. I'm not sure he did, because Galileo already noticed the principle of equivalence, and he talked about. I like the one of the fireworks. He says he describes his fireworks go out, and they make this beautiful sphere of sparks. As it falls, it remains a sphere. You can get rid of gravity by free fall, locally. I mean, he's very explicit. not just the big rocks and the little rocks, and why the feather doesn't because of air resistance and all that. I mean, he was right. But, of course, you needed special relativity and make that into a four-dimensional space-time, as Minkowski did, and then bend it as Einstein did.
So the collapse and gravity come in?
Nothing there. But my argument is that the principle of equivalence, which is the basis of general relativity, is in conflict with the principle of superposition. And the argument is more or less this. I say, think of an experiment done in a lab on a tabletop, and you want to take the Earth's gravitational field into consideration. Now, there are two ways you might do this. The way any sensible physicist would do it, you put a term in the Hamiltonian. If you don't know what that means, don't worry. Put a term in the Hamiltonian for the gravitational field and just chug away, the usual procedures. Fine. Then you notice that Einstein's sitting in the corner, or Galileo even, and tell you, no, you shouldn't do it that way. The gravitational field of the Earth is locally just like free fall.
Mm-hmm.
So you can consider your lab, your coordinates are falling, and the lab is just accelerating in this thing. And there's no gravitational field. Okay, you do it this other way. It's a different way. Different coordinates, you do it away, and eventually you come up with almost the same answer. The key, of course, is in the almost. The wave function you get is just the same, except for the complex multiplier, the phase factor,
right,
if you like, which people would quite like to discard, because when they're going to measure anything that you observe, they're taking amplitudes, you take squares of moduli. So you don't worry too much about that. Until you look rather too carefully at this actual factor, which is different between these two procedures. That actual factor involves the time, an exponential of the time cubed. And that is not that serious if you really think of it. If you're thinking of quantum field theory, that's serious because that's telling you that's a different vacuum. You're actually working in a different vacuum. So you might say, well, you still might say, who cares? Because you say, stick to your vacuum, and you get the right answer at the end. Okay. So I'm going to change the problem a little bit, rather seriously, actually. I'm going to say that in this experiment, there is a lump of some sort.
Okay.
Which is put into a superposition of two locations. So it's a little stone, which goes into two places, or a little bead or something, which is part of the experiment. Now, I try to use the Galilean Einsteinian perspective, and I ran into trouble because as I get close to the bead, I see whether it's here or here, I can't get rid of them both at once. And that's, of course, the Einstein problem, which led to general relativity. I can't get rid of them both at once by free fall. So what do? I do what any sensible physicist would do. I cheat. I say, okay, I know I should be using the Einstein perspective, but let's just try instead measure the mistake that I'm making by adopting that, by the Newtonian perspective. So I adopt the Newtonian perspective, but keep track of what might be a little error in doing it. Then I integrate that error over space, and I do a little integration by parts and some little bit of fiddling around with it, and I get with an answer which looks like a uncertainty in the mass of the system. It is the mass of the system, but it's not the fact that it's a superposition. It gives me an uncertainty of that mass. Now I can measure, and now the thing is that's a bit like particle physics, where if you have a decaying particle, its mass is not completely well defined. It has an error, a fuzziness in its mass, which is given by the Heisenberg time-energy uncertainty principle. So its lifetime, if it's an unstable particle, is inversely related to this sort of fuzziness in its mass. Now here I have a fuzziness in the energy of the system, the mass energy of the system. So I say that's the reciprocal of that in natural units is when I say natural units, I mean making all the things equal to one that you can do, as Dirac sort of initially pointed out, I guess. And I get the formula, which Diósi had already discovered a couple of years earlier than me.
Right, for different reasons.
I didn't know he'd done that. It was a different argument. But I thought this was a nice argument because it just revealed the tension between these two very basic principles, principle of equivalence and the principle of superposition. And they're a bit in conflict with each other. And the resolution of this conflict comes through allowing your unstable state to collapse into one or the other. Now, it's what you only get from this way of looking at it is an uncertainty in the mass. And I know that Yvette's looking directly at this thing rather than looking at the collapse, which is a powerful thing to exploit.
And just for people who are wondering about Yvette Fuentes, there's a podcast on screen right now where we go into 2 hours in depth into this topic. Now, do you have a mechanism for why or how gravity collapses the wave function? Or do you just say it has to, a collapse has to?
That's where the new theory has to come in. I'm just saying, look, I have a problem, I need a theory. No, all I can say is that it tells me how big the factor should be. You see, it tells you, you can measure this uncertainty, and it's not so hard. You just think of the bead that I was looking at. Imagine there are two copies of the same bead, and I move it into this superposition, and I ask how much energy would that cost me where I ignore all forces except gravity. Very tiny usually, but it's nevertheless, it's enough to collapse the state for even a flick of dust will collapse in a very short period of time. So it gives you that much. And it's the same as Diósi. It's the same formula. It's not a theory in the sense that his was. I mean, I think his ideas got, as far as I'm aware, rather shot down by the Gran Sasso experiments. Was it? There's the thing, they took this thing down a mine shaft or something. No, it's to do with the heating. They anticipate bodies spontaneously heat, which I don't want. That shouldn't happen. But that's because the collapse has a very curious... You see, if you want to make it consistent with special relativity, don't worry about general relativity at the moment, you're really already in trouble. Because you imagine a body splitting, it's the superposition. It's not two bodies. It's one body, superposition of here and here. They get very far away from each other. They haven't collapsed yet. And now they're going to collapse. One goes. In whose frame does that happen?
Mm-hmm.
Is that a frame you should be talking about? How do you make that consistent? Well, what you've got to do, I'm not worried about that. Lots of people seem not to worry about that. I'm worried about that. You say, okay, the only thing you can do, which is relativistic, I mean, there are other wrong routes you can take, which I won't go into because it's quite a bit of a more story than I'm making out here. The only route you can take is to say the collapse actually took place right back to where the split initially took, and then there was only one route. But what about the other route? Well, what I have to do is to describe things in terms of two different kinds of reality. One of them is quantum reality, and one of them is classical reality.
So one doesn't give rise to the other? They're actually separate?
Well, it's the quantum reality, if you like, which does give rise to the way that the classical reality behaves, but it does it in a kind of retrocausal way. So that's what's so confusing.
In a kind of retrocausal way? Or is it retrocausal?
It's kind of retrocausal.
Okay, explain.
I'm saying this deliberately because it's only quantum reality. You see, this is a puzzle I think it was a puzzle I had, and you can resolve this in a rather peculiar way. You might say, oh, sure, if it was retrocausal and it went back to the beginning, then how do you, what am I trying to say? You can travel faster than light. Yeah, you can travel faster than light or backwards in time or something. Sure. So I've got to tackle that problem. Or you can signal backwards in time. That's the thing.
And you were trying to retain special relativity before.
Because I'm just saying you can't do that. Because, you see, think of Alice and Bob. I had this in some notes which I circulated, but I don't think it was actually published. It's sort of pseudo-published. You see, I have a book the book I wrote, which was with the Princeton University Press, called Fashion, Faith, and Fantasy in the New Physics of the Universe. The fashion was about string theory, which I'm not sure was still so fashionable now, but it was then. Faith was quantum mechanics at all levels. And fantasy actually had to do with cosmology. It was to do with inflationary cosmology, because I simply thought inflation is much too fantastic. That's another story. But the fashion, so I had to write this new preface. They're going to bring it out. It's out now. I think it's almost out now. A new printing of Fashion, Faith. I wasn't allowed to change anything in the book, but I was allowed to write a new preface. And I do give an outline of this idea. I think I do. The retrocausal thing. You see, the thing is, think about the standard EPR. So you have a spin zero state, splits into two halves, spin half, and Alice takes one off in the spaceship and Bob takes it up on another half. Alice makes a measurement. What do I say happens to the quantum reality? It's a quantum measurement. Quantum reality propagates along the path light cone. What could be crazier than that? The backwards way, along the path light cone. It hits Bob's world line way earlier than he does his experiment. So his state is already changed into the one which is the opposite of Alice's state. Bob makes his measurement later. He doesn't know what the state is. Alice can only communicate classically with him. This is a quantum information. Now, quantum reality information. Quantum reality, you cannot measure, you can only ascertain.
Explain the difference between ascertaining and confirming. Because when you were on stage with Sabine Hossenfelder, you said, you can confirm at, I think it was the classical level, you can confirm.
And you can confirm.
Whereas at the quantum, you can ascertain. Like you can ask a question.
That's right. Well, you see, that it's really Einstein. It's Einstein's fault. Because he was saying, I think a lot of people were worrying about the reality of the wave function. Is it real? Is it really there? Not real. It's complex, you see. It's not real in the sense of real numbers, but is it really there? And Einstein produced the statement. He said, well, a concept of reality is introducing, which is if there's a measurement you can make on the system without disturbing it, and which with 100% certainty gives the answer yes, then that measurement is revealing an element of reality. So he says that the quantum state is real in that sense. What he didn't say, as far as I'm aware, is that is quantum reality. It's not classical reality. Think of the spin of a spin half particle. I think I always like spin half particles.
Sure.
It's the simplest thing to say. Spin up and spin down, if you like, or spin right and spin left. Suppose its spin is about that way. If I know through its origin, where did that spin come from? Oh, yes, I know. Oh, it should be spinning that way.
Wait, sorry. Is this a hidden variable that it's carrying with it?
It's not hidden variables. Forget about Bohm.
Forget about Bohm.
I had
You're not a fan of
endless arguments with Basil Hiley on that topic, and I prefer not to go back there when I was at Birkbeck College.
All right.
Let's not talk about hidden variables. If you can call them hidden variables, you can, but that's not my idea. It's not that.
Got it.
It's quantum reality. So this state is that, but it has a quantum reality of spinning right-handed about that particular direction. And we know it is because we've set up and we've produced it in that state. You could do that by some experiment, and it comes out in that state. Now, I'm going to use Einstein's criterion. I can measure the spin in that direction using, as long as it's got a magnetic dipole or something, I can measure it, and I can, if I've got it right, every time I measure it, I will get, or I can measure the same experiment many times over. 100% certainty, that's real. That's what Einstein said is his element of reality. I'm just slightly modifying what he said. It's an element of quantum reality. It's not classical reality. I can't say to the state, hello, state, which way are you pointing? It just looks at you blankly. It says, I don't answer questions like that. Give me a better question, you see. If I say, are you spinning that way? It can say no or yes. If you say, which way are you spinning? It doesn't answer that question. That's a quantum reality thing. Quantum reality you can't ascertain it. That's when I say you can't ascertain. You can't ascertain which way it's spinning. However, you can confirm which way it's spinning by the Einstein criterion.
I see.
Now, if Alice and Bob, you see, if Alice propagates back in time, Bob's state is already, in a certain sense, the opposite of what Alice is going to measure. But Bob can't ask the state, which way are you spinning? If he could, then you could send signals faster than light. The whole of special relativity goes down the tubes. The whole of modern physics does. So that's not a good idea. So quantum reality, sure. Bob can't say, he can ask it. His spinning state says, don't ask me such a question. I don't answer questions like that. Suggests a direction. So he does. He suggests a different direction. He has no idea what Alice has spun. I did worry about this quite a lot by saying, can he ascertain which way Alice is measuring it, and even if you don't know which answer she gets? So there's a bit of a subtlety there, because she might orient her apparatus in some way, and does that information somehow, you want to make sure that can't be ascertained by Bob either.
That she's free to choose independently?
She's free to choose. She says, yeah. But she might say, I think I'm going to choose that direction because Bob's keen on that direction or something, and that will tell me I'm happy. See? No, she can't do that.
Have you thought about free will?
I've thought about it. In fact, I thought about it even quite recently. First of all, I think it's a useless kind of thought because even though, you see, Stewart is very keen on free will because he says that the theory of microtubules and all that stuff gives a room for free will. See, maybe it does in a way, but you see, often people say, well, it's all determined anyway. And I think people get a little bit confused. You see, I going back to my experiences I used to have when I was very young, and my younger brother was even younger, and he could always wallop me at this game, scissors, paper, stone. And I thought, how can he be walloping that game of chance?
Right.
So to make sure it was a game of chance that he couldn't wallop me at, I went into my father's study and I got out a book of logarithms and went into the middle of it and got out the string of numbers and produced which way you went by the string of numbers, followed it very carefully, and he couldn't beat me. So I thought, thank goodness. He's not reading my mind. It's just that he gets recognizing patterns and things like that. He's good at that. Maybe even unconsciously. He recognizes patterns and he knows which way I'm going to do next because I'm not really being random. So it's not randomness.
Yes.
The free will is not randomness. So what is it? You see, I think it's probably, you're free to do something which may be very well determined. You see, do I take course A or course B? You may be in some meeting, you see, which making decisions about some big plan. And you want to know, what is the consequence of doing A or B? Well, then you rely on your understanding of which is the right thing to do. So free will, it might be the same as somebody would do just by chance. That's not the point. The point is that you've used your consciousness as something to employ in making your decision. So that's what free will is for, in a sense. I don't know if I can say much more. And I also get impressed by things when I hear things about bees, and they're unbelievable.
Yeah.
And they seem to play...
They're unbelievable.
Unbelievable. Yes, well, they sort of, they play football. There's some thing they were telling me about they're not trying to hunt for honey. They do things in little balls and they kick them around. There's some kind of football that they play. Why are they doing that? For fun? That would mean they have to be conscious, doesn't it? Maybe they are. I don't know. I don't have a view on this. I do believe that consciousness goes way down in the animal kingdom, sure.
Is the universe discrete or continuous?
I used to be very keen on discrete. I did it. Yes, people told me, I got to go into anecdotes. I'm too old. I just talk about anecdotes rather than the physics.
Okay.
If you want an anecdote, I can give you an anecdote. I used to be very keen on discreteness. There were two things in mathematics that I thought, these are the nice things for physics ultimately to be based on. Combinatorial things, or maybe complex numbers. And I think I sort of at that time thought combinatorial things.
I'm surprised if you came from algebraic geometry that you would be more keen to the finite side, the discrete side.
I probably was at that time. You see, I had a sort of gradual conversion. I think the conversion came with David Finkelstein. When, as he said after his talk, he gave this talk that Dennis Sharma took me to when I was a research fellow at St. John's in Cambridge. And we drove to London to hear this lecture given by David Finkelstein, which was on the Schwarzschild horizon, which is not a singular, is a horizon.
Sure.
And he described that. And I found that amazing. I thought it was very beautiful. At the end of the talk, I had a long chat with him about spin networks. So I described the spin networks to him. And he told me afterwards that at this meeting, we swapped subjects. I did general relativity from then on, and he had been doing GR. He swapped onto combinatorics. I consider I got much the better deal. But that's, you see, I was thinking about combinatorial things, and spin networks were very much that kind of thing. Can you not think about the complex numbers which give you the directions of spin for a spin half particle, or do you instead think about this network, which is really the important thing, and the direction comes out of the network? No, I was playing with that idea.
You said you've changed your tune now to be on the more continuous side or continuum side.
The power of complex analysis was the other thing which had impressed me. And it's more drifted onto that side.
Do you think the continuous lies at the classical level and then the discreteness lies at the quantum one? Do you think that's the way to quote unquote unify them or harmonize them?
I wouldn't say anything like that maybe. There's something, obviously there's something discrete in quantum mechanics. Something which people used to think was continuous, shock, is actually discrete.
Now, speaking of what people used to think, you used to think that AI couldn't do what mathematicians do. Do you still hold that view because of their limitations, their formal systems?
In a certain sense, yes. You've got to be a little careful about these things. But I was hearing just recently, I think it was on Zoom talk.
Yeah, the remarkable 0-1 model or 0-1 model of ChatGPT, yeah. What would be an example of something mathematical that you think a computer could never do this?
Well, it doesn't do anything. You see, you've got to tell him.
Well, even if you put it on play, you just press play and you say, generate for me some math. Because if it's the autoplay that's the issue here, that's easily solvable.
But there's a confusion, I think. It's also important to me. See, because one of the talks that I attended when I was a graduate student at Cambridge, nothing to do with what I was doing, was a talk by a man called Steen on mathematical logic. And I learned about notion of computability. I learned about the Gödel theorem. I found it stunning because what it told me, you want to prove something in mathematics. How's this statement? What the Gödel theorem says, it says, I am not provable by your methods. Yet I know it's true. Why do I know it's true? I know it's true by virtue of my belief that the proof procedures only give you truths.
There is the idea that people can brain upload. That is, they can take your consciousness and put it onto a computer.
No.
What are your views on that?
I'm saying no on that one, definitely. If a computer, when you say the word computer, you have to be saying what I mean by a computer and what Turing meant by a computer, which is a computational system. So if it's that, no is the answer. If you're talking about a physical entity, which is not an animal or not a living being in our ordinary sense of the word, maybe. But it has to take advantage of what we're taking advantage of without even worrying about it, which is presumably, here I'm going way outside of what I know, but I'm saying it's whatever the physics is which governs the collapse of the wave function.
Right.
Now, that is not quantum physics, because quantum physics doesn't have an answer to that question. It's this physics which combines GR with quantum mechanics. Maybe it used multi-twistors for all I know. I have no idea. It would be very nice if it does.
Do you think if quantum theory was not to be modified, then the many worlds interpretation is the way to go?
It would just be wrong. I'd say it can be any way people believe in, stick to quantum mechanics, that wrong theory, then they would have to go that way. But I don't want to go that way because I want to go the way that the world goes.
Oh, what I mean to say is, do you think quantum theory as it stands implies the many worlds theory?
Trouble with quantum mechanics doesn't say anything about the many worlds theory. Yeah, in a sense, yes, because it says all these things are in superposition. But I'm not quite sure what the many worlds theory is, because it can't be just that. Otherwise, I wouldn't see just one world. So what is the rest of the theory, which tells me that I only see a limited proportion, that maybe they're in superposition, but not many. Certainly not as different as they could be. I don't see all these alternatives. Now, is that to do with this little creature crawling through this multitude? Now, why doesn't this partner creature going off in another branch doesn't explain anything?
Recently,
I'm just saying it's wrong. You're trying to say, if I believed in quantum mechanics, yes, but then I can believe in a wrong thing and I get another wrong answer. I'm just being my rude self to say that quantum theory is wrong.
We like that on Theories of Everything. So, you were recently speaking to Bernardo Kastrup about idealism, which is about consciousness as fundamental. So maybe you don't recall, but it doesn't matter. The point is, some people believe consciousness to be fundamental.
Oh, was this a video thing?
Yeah.
No, I think I did recover that, yeah.
Okay.
Yes, I think he was saying things which seemed to me orthogonal to what I was saying.
Okay, so please recount your views on, is consciousness fundamental?
Yes and no. How's that for an answer?
A superposition answer.
It depends at what level you're asking this question. I mean, if there were no consciousness, I can't see. You see, a question like this has to have a framework. You see, I'm talking within a certain framework of theories.
What's something that you used to be dismissive of when you were younger, that you used to disregard, repudiate, and
Many
now
worlds theory.
as you're older, that you're more open to it?
Oh, I see. Oh, no, I'm worse. I've got more narrow-minded as I've got older.
Interesting.
Oh, yes. I'm terribly narrow-minded now. I'm prepared to listen to other things, sure. But no, I think CCC is right. I think that collapse of the wave function is right, and it's a gravitational effect.
Can you talk about that, about the CCC?
Now?
Yeah, just briefly, if you don't mind.
Sure. Well, it was one thing when I was saying fashion, faith, and fantasy. The fantasy was inflation. See, I don't believe in inflation.
Right.
The current view of cosmology is that the very early stages of the universe, first tiny fraction of a second, there was this inflationary phase, which was supposed to have smoothed out the universe, and that's why it seems so uniform. Now, it's a load of poppycock as far as I'm concerned. I don't know about that word to use here. It's probably poppycock's fairly mild. Because if you reverse time, it gives you the wrong answer. I mean, what black hole singularities are any theory which would iron out singularities should iron out the singularities in black holes. They're completely different. The singularities in black holes are absolutely wildly diverging via curvature. The singularity in the Big Bang was an extraordinarily special event. I haven't seen any explanation of this. I mean, I had various wrong explanations of my own. But they weren't, well, I thought that maybe quantum, yes, when you have quantum theory, I was trying to say that singularities had to be one way around.
What would you like your legacy to be?
So it's really fairly equally split, I think, between CCC on the one hand, the cosmological picture, and the wave functions. You see, the theory there is not developed enough to anything there. It needs much more. You see, the theory, that's more twistors and their offspring. And I'm hoping that, you see, when I talked about talked to too many people today. And did I talk to you about the product of three vectors? I did, didn't I?
Yes.
Yes. You see, you multiply, you have in twistor theory, in bi-twistor theory, you have a product of three things gives you a fourth. And this is useful if you want to talk about split octonions. But there's another thing which might be useful for. Those three, it's really the span of those three things. It's like a vector product. It's not it's you lost the vectors. It's really the span of the two. It's the way you talk about the plane. So with the three things, it's the way you talk about the three space. Now, that's awfully tempting to me to think that that might have something to do with strong interactions. That it's the SU3. That's where the SU3 resides. See, in one of my conversations with Feynman, they're all stories, and each one is a nice story. But I had a conversation with Feynman, which Stephen Hawking had organized, and he was a bit grumpy because Stephen had disturbed his holiday. But anyway, and I was trying to describe twistor theory to him. And then I was trying to describe how you might describe particle physics in it. And he said, don't follow that route. He said, what I said about twistor is very interesting. Yes, keep that going. But don't try to follow that particular route towards particle physics. That's wrong. That's not a fruitful route. And he was completely right. That was wrong. It was much too early. So we tried to do particle physics with twistors, putting a few of them together and all that. And I think that was wrong. I think he was right. He was right that I was wrong. However, doesn't mean that the thing with beta, it's much more like it's more like SU3 because you really don't care where the vectors are. It's the space. And it's a way of attributing another entity to it. I don't know if I can say what I mean. It's a bit more like the other exact gauge theory there is in physics, which is electromagnetism. And you do have a thing like this in bi-twistor theory as well. You have this thing which I call multiplying by I. I needed that as well. So it's a circle. So you have this circle and you have this three-dimensional space.
The question is, what do you want your legacy to be?
Well, I say it's a twistor theory, you see. But CCC is quite a good one for a legacy, I guess, because it does change our picture of cosmology completely.
Do you believe it to be the case, or do you just posit that as a possibility?
Look, it's a completely different story. In this case, there is strong evidence that nobody pays any attention to. But I say nobody, not quite anybody.
About conformal cyclic cosmology.
Yes. We see these signals. I mean, there is a nice wrongness about them too.
Okay.
But the wrongness is just a factor of two. All these are anecdotes. As I say, I'm too old to do physics. I just do anecdotes. No, I had not Zoom. This was just email communication with Alan Guth about
cosmology.
Yes, that's right. And he was telling me about, I would give him all the credit. He put our boots on and followed exactly what we should do in our calculations. And he said, your calculation of how big the Hawking points are, these are spots which we claim are there in they're observed with strong observational, 99.98% confidence level. Particle physicists tell me that's much too small a number. I mean, you need much more confidence level than that. It's only about 3 sigma or something. I don't know what all that means, but that's what they tell me. But still, for cosmology, that's pretty confident level. And these spots are there. They're all the same size. They're all about 8 times the diameter of the full moon. Alan Guth tells me, you're wrong. They should be 4 times the diameter. He doesn't tell me the diameter. He tells it in terms of radians or minutes of arc or something. I forget what that means. So I'm used to the full moon. I'm using my low-grade... they're only 4 times. He said they should be 4 times. So I email Christoph and I said, look, Alan Guth tells me we got the wrong size. They're not 8, they're only 4 times. Christoph tells me, no, that can't be right. I go and check, but he's just made a mistake. He comes back to me. He's right. They should only be 4 times. So we have to do something with our theory. We have an idea what you should do. It doesn't change the whole scheme. I mean, ordinary cosmology doesn't get them at all. Getting just a factor of 2 wrong is mild. It's minimal. And they're seen both in WMAP and in Planck. I'm only counting the ones which are strongest and which are the strongest ones, which are the same ones are seen both in WMAP and Planck. There are 5 points. When I say points, there are these little spots in the sky, 5 of them, which we see in exactly the same places in WMAP and in Planck. Confidence level, calculated by Christoph, because I don't know how to do that kind of thing, 99.98% confidence level. People contact me and say they don't believe us. Well, people say, no, I've done the calculus all by a different way, and I only get 95% confidence level. Okay, well, you could use your method if you like, but that's not interesting to me.
You just outlined how you'd like to be remembered in physics, and I'm curious how you'd like to be remembered as a person.
As a person. Not too much of an idiot, I hope. Well, look, there's a book coming out any minute. I better read it first. And I'll see how it tells me how I might be remembered by people. I don't know.
Who's taking on the torch that you're passing? Who are the people?
Yeah.
And what is that torch? Briefly speaking.
Well, there's more than one of them, you see. There's one in twistor theory. I don't know who's carrying it on twistor theory, because it's gone. You see, if I'm talking about twistor theory, there's 3 versions. You see, the answer is there's pseudo twistor theory and twistor theory and pseudo twistor theory.
Okay.
And the pseudo twistor theory done by the mathematicians, which is all positive definite space.
Sure.
The pseudo twistor done by Ed Witten and company is got two time dimensions and 2 space dimensions. Those are pseudo because the dimension is wrong. Mine has got 1 time and 3 space. So I'm calling that the real twistor theory. Now, the number of people doing real twistor theory is not very big. The ones who do pseudo twistor theory is quite huge, particularly the mathematics people. It's quite a big subject now. But it's not my twistor theory because it's still pseudo twistor theory.
What's your advice to students who are getting into the field of theoretical physics? And what are your views on academia as it stands now?
I think there's probably too much domination by things you do on computers. I'm not quite sure what I mean there. I don't know. I mean, I don't know most of what people do in physics, and I can't really comment. So I can't be rude about it. It shouldn't be rude about things I don't know. I think it's difficult to shake cosmology. I've noticed that in cosmology. You see, this is a scheme, I'm talking about CCC now, which is not taken seriously simply because it's too outrageous. It is outrageous. So if somebody had mentioned it to me before I thought about it, I might have thought it's not worth thinking about. I did even have a session with Stephen Hawking, me and Stephen and nobody else, and I described CCC to him. I don't know what he thought of me. He came away without saying a word. Though he asked me one question which showed he didn't completely understand what I'd said. So I tried to get that straight. I don't think he believed a word of what I said. What do I do? Well, it's outrageous. The theory is outrageous. I agree with that. Doesn't mean it's wrong. There's evidence for it. And it solves the problem of the specialness of the Big Bang. Nothing else does that I've seen.
Now, just imagine you're speaking to students and they want to know, what advice do you have, sir?
I think when people ask me that question, apart from being completely flummoxed, I say, do what excites you. I mean, you have to concentrate. In doing physics or research in general, you have to have your area which you concentrate on, but you've also got to have a broader area. So it's a bit like a funnel like this. You go way down, deep in the area you're interested in, but you should keep an interest in what's going on all the time as well. So don't shut your eyes to what the rest of the world. You may see a connection which nobody else has spotted.
Thank you, sir. It's been a pleasure.
Thank you.
Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. There's now a website, kurtjaimungal.org, and that has a mailing list. The reason being that large platforms like YouTube, like Patreon, they can disable you for whatever reason, whenever they like. That's just part of the terms of service. Now, a direct mailing list ensures that I have an untrammeled communication with you. Plus, soon I'll be releasing a one-page PDF of my top 10 toes. It's not as Quentin Tarantino as it sounds like. Secondly, if you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Kurt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate toes, they disagree respectfully about theories, and build as a community our own toe. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, toe listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/kurtjaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on Toe full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.